Greetings everyone. I'm proud to be presenting our work on enhancing road safety with cost-effective wireless technologies. Our work consists of primarily a pedestrian detection system, which is a subsystem of the project we call Active Road Sign System. I'll go into details about the methods and the architectures of the complete system and present a cost comparison against the traditional systems. I then conclude with the applicability of the active road signs. The existing road safety system uses signs placed at roadsides and lights to convey information and warnings to the drivers and pedestrians. However, these signs are often unnoticed by the affected parties. Also, having static road signs leaves the transport system unoptimized. This is resolved by deploying intelligent transportation system. Intelligent transportation systems can convey warnings and information to drivers and pedestrians more effectively by keeping the quality of information higher than the existing systems, as they can provide adaptive information and better optimize the system. These existing ITSs are mainly enabled by dedicated short-range communication and cellular V2X communication technologies. These are extremely expensive with low penetration in the market. Hence, they lack vehicles that support these technologies. Therefore, we are designing an alternative system which can coexist with DSRC and CV2X to deploy ITS applications. The lower cost of the design system makes it a viable solution for retrofitting also. We are using this technique to develop active road signs applications. Active road signs is a system that acts on the inputs generated relative to its surroundings and allows to alert pedestrians and even in the interior of vehicles within the vicinity. These active road signs can be described as static signs that are placed on roadsides, or dynamic road signs that change depending on the surrounding influential factors such as traffic lights, or semi-dynamic road signs such as slippery roads signs or roadwork ahead signs.
You can turn right. You can turn right. You can turn right. You can turn right. Pedestrian crossing ahead. Pedestrian crossing. Speed limit 50 kilometers per hour. Pedestrian crossing. You can turn right. You can turn right.
One of the applications being developed is a railway warning system using the coexistence capability of the naval system with DSRC. We equip the railway vehicles with DSRC transmitter, and a retransmitting device is used to receive data from the railway vehicles and convert them into Wi-Fi messages. This is then passed on to vehicles which are about to cross the railway. If required, the range of the system can be extended using Wi-Fi extended devices using a multi-hop mechanism. As presented here, another such application is to detect pedestrians crossing the road. This information is forwarded to the oncoming traffic using the Wi-Fi based communication system. As a start, with pairs of transceivers placed as shown, introduction of disturbances caused due to obstruction in the signal passing between the free space of the transceiver pair are interpretable. This interpretation is done by observing the channel state information of the signal. The information, formerly known as CSI, can be used to estimate the type and number of obstruction with relevant complexity of processing. With this concept, we introduce pedestrian counting, where the number of people waiting at a pedestrian crossing can be determined. By using two Wi-Fi transmission-enabled devices as receivers coupled with their transmitters, UDP packets are transmitted between them at a rate of 25 Hz. With the help of ESP-CSI tool, channel state information is generated and passed along the serial interface to a processing compute unit. Within the processing unit consists the acquisition and the pre-processing of the CSI data to ensure the information is isolated against the external noise factors. Once data is concatenated relevantly, a deep learning neural network of one-dimensional ConvNet is trained to determine how many pedestrians are waiting at the crossing. Here's a table that shows our evaluation process of 7 different items labeled as experiment ID. The max count shows the total number of pedestrians we set along with the accuracy and precision of our model ConvNet against a commonly found MLP with their respective results for each of the 7 experiments.
For the pedestrian count estimation, the used setup is shown in this picture. As we described on the presentation, CSI values which contain amplitude and phase information are obtained from the two ESP32 devices in the RX side. This is a CSI plot for various 1-second outputs during the pre-processing stage. Each color denotes a different sample in the dataset during the 1-second period. Starting from top left corner, you can see the original phase, then the unwrapped phase, sanitized phase, and the exponentially weighted moving average filters phase. On the last row, original and exponentially weighted moving average filtered amplitude can be seen. The final filtered outputs are then fed into the deep neural network as described during the presentation. As you can see here, when CSI amplitude and phases are plotted corresponding to the pedestrian count, each plot is visually distinguishable from each other, proving the fact that pedestrian counts can be estimated by CSI information.
Here you can see the app UI. It contains a plot which indicates the variation of the ground truth and estimated pedestrian count. Also, it dynamically updates the current ground truth and estimated pedestrian counts. Now let's run a script in the local machine to post sample test dataset to the endpoint of the Dash app to emulate a real pedestrian waiting scenario. Sample data are posted in such a way that the pedestrian count will be increased gradually from 0 to 12 as in a real scenario. Now you can see data being posted through the local computer and Dash app getting updated.